Okay, so good morning, everyone, and welcome to today's webinars. The subject of discussion for today will be thermal analysis of autonomous vehicle electronics. The presenter for today's webinar will be Richard Ozaki. He is the field application engineer from Siemens, and my name is Keng Nguyen, and I'm a field application engineer from EDA Direct. Um, so, Richard, next slide. So we have been in existence since 2007, 1997, and we've been supporting customers in the various industries with various tools, design service, and we have built over the time a lot of expertise in areas like signal integrity analysis, design visualization and analysis, such as today thermal mechanical design and things like that. So we're familiar with the market and working with a lot of customers. Next slide. In terms of the vendors that we represent, as well as providing technical support and sales, we have Mentor Products and Mentor, which is now part of Siemens company. And on the Mentor side, there are tools that we can help customer in doing simulation for FPGA ASIC design. There are layout tools, and also for manufacturing with Valor, signal integrity analysis, and today we're talking about thermal analysis. There are also tools that help customer doing requirement tracing um, on the Mentor side. And then on the Siemens side, there are mechanical tools that complement the PCB offerings that we have. And that include mechanical design tools such as NX and Solid Edge, structural analysis like FEMAP, and other vendor that we have for chip and ASIC design, as well as visualization of RTL. Next slide, please. In addition to providing tool sales and support, on occasion we also provide analysis service and training to customers who would like to go deep down in any one of the tools that we sell. And that includes things like signal integrity, power integrity, thermal analysis, PCB layout, schematic analysis for your design, as well as verification for chip design, FPGA, and ASIC. Okay. And with that, I'd like to hand over to Richard to continue with the presentation on the topic today.
Okay, thank you very much, Kung. Before I jump in, just a brief introduction on myself. My name is Richard Ozaki. I'm a field application engineer for Siemens PLM based out of San Jose, California. My specialty is in CFD analysis for electronic systems. So whenever you have airflow or thermal issues related to electronics and cooling electronics, I can provide training, consultancy, that sort of thing within the Siemens group. So when we think about autonomous vehicles, if you ask someone in the 60s maybe what a self-driving car would look like, they would probably say something a little bit like this, a robot in a car that drives you places. And that's a very quaint idea, but I think the reality is that in the last 10 years or so, autonomous vehicles are becoming companies related to autonomous vehicles are really booming, especially here in the Bay Area in California. And there's lots and lots of research and startups related to autonomous vehicles. So autonomous vehicles, they do have a lot of different requirements, from things like sensor packages, processor packages, and drive lines, as well as things are becoming more electrified. So there's a lot of considerations to take into account when designing autonomous vehicles. And purely from a thermal analysis perspective, we're going to be seeing large amounts of heat generated as all this data needs to be combined, consumed, and then passed through to a central operating system and algorithm to actually decide what the car should actually do. So if we look at some global statistics, by the year 2022, we should see 99% of cars should have automatic emergency braking. right? So all new cars from 2022 will pretty much have automatic emergency braking in the US. By 2035, we should see about a quarter of all new cars will have partial or full autonomy. Partial autonomy, think of the Tesla system where it can actually drive for you on highways, but you still need to take manual control in the city streets. And if you look at this Cisco survey, 57% of consumers globally trust driverless cars, even more so in emerging markets. If you look at Brazil there, so really the pace of design and the speed of which innovations and these products are being actively researched and should be coming to the market in a not too distant future, which is great for us here at Mentor and Siemens, because that opens up a whole new market for thermal analysis. So let's have a basic look at an overview of the basic structure of any autonomous system. So autonomous broadly comes under the term ADAS, Advanced Driver Assistance Systems, and there can be a wide range of different sensors that can feed data into the sensor fusion box. Radars, LiDARs, cameras, all of these will have different inputs which need to be combined by the sensor fusion box. There's also going to be other sensors, which might be things like GPS. They could be communicating with other autonomous vehicles to expand the range of the sensors. So all of these inputs, raw inputs, are fed into a sensor fusion box. The data is amalgamated and processed, and then that gives a clear image to the ECU as to what's happening around the car. And then the ECU decides what to do, whether to steer, to brake, emergency situation, etc. So what we're really interested in is the left-hand side of the graph. So the radars, LiDARs, cameras, and also the sensor fusion box as well, which we'll come to very shortly. So during this demonstration, we're going to be looking at a few different types of autonomous vehicle sensor systems and sensor fusion systems. So we'll first of all have a look at a LiDAR in natural convection and seeing what some of the challenges are going to be in LiDAR. We're then going to be looking at a front-mounted LiDAR transient ramp-up time. So what happens when the vehicle is sitting at a light for maybe, say, 5 minutes, look at the temperature change of that unit, and then once the vehicle starts moving, what is the delta, the time delta for the device to start cooling down as well. Kang, can I ask you to mute all the participants, please? And then next we'll be looking at a roof-mounted LiDAR solar irradiation model. So this is a little bit more complex geometries where we've actually got some solar loading and looking at the effects of the electronics within the roof-mounted unit. And then finally, we'll be looking at a sensor fusion box, which is boards with components, which is going to be processing the data at a very high rate, mounted maybe in the trunk or maybe even under hood, which can get very, very hot. So first of all, let's have a look at the LiDAR unit. So LiDAR systems, this is a very small unit. This is about 3 inches by 2 inches, looking front onto the unit. But it's a solid state part, so there's no moving components within a LiDAR system. And some of the thermal design constraints are that it's an enclosed environment. So it needs to be IP67 rated. It cannot have water or dust ingress. And there are IC components within there that need to be kept cool for reliability purposes. And there are certain things that we can do to increase the heat transfer coefficient on the outer surfaces of the LiDAR enclosure, such as adding heatsink fins or even thermally connecting it to the chassis of the vehicle, for example. So we'll have a look at some of the things that we can do with a LiDAR unit. So if we look at the internal details of this LiDAR, this is something I've just pulled from the internet. We have 3 main PCBs in our LiDAR detector. So here we have the front one with all the sensors, and then you have a central board, and then the rear board has got most of the high power components, 2 BGA units, dissipating up to 3 watts. So there's only really about 7 watts total dissipation in here, but there's still some thermal considerations you need to take into account, especially high power components. These need to be thermally contacting some sort of heat spreader or some way for conduction to occur, thermal conduction from the hot components to the outer casing of the LiDAR unit. But we're going to have a look at 3 different scenarios. So what happens when the LiDAR unit has no fins, when we add some horizontal fins to take advantage of the forward motion of the vehicle, and then maybe some vertical side fins as well to take advantage of the natural convection when the vehicle is in a stopped condition. So we'd like to understand what the best is going to be. So the first image on the far left, this is our baseline model. This does not have a heat spreader at all. And you can see that the highest temperature is reaching all the way up to about 105 degrees C on the BGA. And that's because it's essentially just 3 PCBs floating in the middle of a box. The heat transfer is dominantly convection. So, and this is again a sealed unit, so the air is convecting on the inside to remove the heat from the components, and we can see 105 degrees, that will not meet our design criteria for the thermals. So next we add a heat spreader. A heat spreader in this instance is just a horizontal aluminum plate connecting the BGAs to the actual aluminum housing of the LiDAR unit, and that gives a conduction path to the edges of the box to really push the heat out to the casing. And bear in mind, conduction is by far the most dominant mode of heat transfer. So if you can get some sort of physical thermal connection to the outer edges of the box, that's always going to give you better results than convection or airflow only. Next, we add some, and by the way, by adding the heat spreader, we go down to 66.5, and that's a huge improvement and well within thermal specs. Adding some horizontal fins doesn't actually do much for the temperature. It actually rises slightly. And then adding some vertical fins, again, doesn't affect the temperature at all. So remember, this is in stationary conditions. So if you are considering adding these fins to the outside of the box, you might not need to. And in fact, the thermal simulation says don't. This is extra machining costs. This is extra parts that have to be fitted together for construction. So in this instance, no finning is required for reliable operation of this unit. And thermal simulation can tell you that quickly without having to prototype anything. So let's have a quick look at the software. But before I do, I just want to talk about one of the products that we're going to be looking at today. So today we're going to be having a look at a tool called Flowtherm. This is a market-leading electronics cooling tool from Mentor Graphics and Siemens PLM, and it allows for the thermal analysis of electronics, which is exactly what we're talking about. Now, just a brief background on Flowtherm. There's 2 main versions of Flowtherm. There is regular Flowtherm, and there is Flowtherm XT, which we're going to be looking at today. They both have their pros and cons, but the first product I'm going to be looking at is Flowtherm Classic. And here we have the actual LiDAR unit with some horizontal fins in here. And what Flowtherm allows you to do, it's a standalone thermal analysis tool. It will allow you to build and create thermal models of your electronic systems. You can see here, it's a 3D modeling tool. It will allow you to create parts. It will allow you to attach materials, heat loads, grid constraints. It will allow you to solve the electronic system and then get a picture of how this is going to perform in the real world. So for example, I can have a look at something like the temperature. So here we have the component colored by, this is a 2D slice through the model looking at temperature. If I was to hide all of the components, let me just grab the root assembly and wireframe that, we can have a look inside the model. I'm cutting through the BGA over here. You can see the sort of temperatures, the air temperatures, the ambient air is at 35 degrees. So you can see the delta increase from the outside to the inside. And then we can couple that with, say, some sort of external temperature map. So let me grab just a moment, spreader. This is the actual box. And if we color this, then we'll be able to get a temperature map on the outside of the box. We'll be able to see where the hotspots are going to be on top of the unit, for example, there, 38.7, only 3.7 degrees C above ambient. And then on the, this is the plastic front, very low conductivity. This is pretty much at ambient temperature there because it's really not very conductive. So it will allow you to get a feel for what the temperature maps are combined with any sort of airflow that might be going over your unit. Now this is actually in a forced convection mode. So what happens when air is passing over the unit, we can understand the airflow combined with the thermals. So let's now have a look at this LiDAR unit. We just had a look in natural convection, and then I'm trying to understand what the transient response looks like. So if we think about a front-mounted LiDAR or radar unit, for example, you can see here a solid body of a car. In reality, it would probably be mounted right here in the grille in front of the AC condenser and heat exchanger packs. Right here underneath the number plate, you're starting to see those. And again, by 2022, I believe, you're going to be seeing these on 99% of new vehicles out on the market. And these are forward-looking radars and LiDARs, exactly as we've looked at here. And as we saw in a image just a second ago, we're seeing the impacts of the forced convection as the unit moves through the air. So we can simulate the airflow onto the LiDAR. So we're going to be assuming that the vehicle is moving forwards at 10 meters per second. First of all, we're going to be stabilizing the temperature under natural convection, i.e. stopped at the lights, and then we're going to accelerate the car up to 10 meters per second and then look at the response time on the electronics. So I've added a slightly more complex view, complex model for the PCBs. So here we can see in Flowtherm, we've created very detailed components. Again, the more detail you add into a thermal simulation, the better your results are going to be. And Flowtherm does allow you to import very detailed models from manufacturers such as Intel, Xilinx, Flowtherm, and AMD, for example, NVIDIA as well. And you can see some BGA devices here that's doing some data processing and capture. So at the end of the, at the start of the transient, we can see the temperatures on the components on the outer surfaces, maybe up to about 70 degrees. And then on the actual components, all the way up to 105 degrees. This will be outside of our design spec. So we may need to rely on some forward air motion to keep these LiDAR units cool. And you can see by the time we've accelerated up to 10 meters per second, the temperature has dropped to 70. But what we're really interested in is how long does it take to stabilize to that new steady state of forced convection. Well, we can see the graph here. This is the front, the middle, and the back PCBs in our LiDAR unit, and we can see the temperature dropping from about 87 down to about 55 degrees C over the period of about 600 seconds or about 10 minutes. So it does take quite a while to achieve the steady state, but again, simulation will allow you to look at this and understand what the transient responses in the system are going to be. Here we have a graph of delta versus time. So initially, as the acceleration occurs, there's actually a slight increase in temperature, and then we have that temperature decrease versus time. Okay, now let's look at a slightly different model. We're going to be looking at a roof-mounted LiDAR application with solar irradiation. So here we have a very simple LiDAR, roof-mounted LiDAR, non-spinning. This is going to be static. We have the housing material, which is made out of aluminum, milled aluminum. We have a transparent window made of glass, and we have some power dissipations within the parts. And we're going to be looking at 3 different scenarios. So surface treatments are very, very important when considering radiation studies. So if you have a very reflective surface treatment, such as, like a mirror coating or a polished aluminum, for example, then you're going to have high reflectivity. If, however, the unit is anodized or painted a dull color, then it's going to have a low reflectivity. So the reflectivity or the surface emissivity of the component is very much going to affect the temperature of the LiDAR. And again, we have the transparent front as well. So when you have a high reflectivity, i.e. 80% of the rays hitting the LiDAR are reflected, then you tend to get you still get a hot spot here, but the temperature rise from ambient is only about 8 degrees. As the reflectivity goes down, you can see the temperature goes up to about 60. And then when you have a transparent window on the front, then you're going to be allowing radiation to pass through, hit the boards, and actually heat those and the air inside. Again, a sealed system, the air inside up, and you're going to be circulating the air as well. So in the first one, because of the reflectivity, the solar loading is 2.37 watts, then 7 watts, then 6.63. And you can see the variance in the temperature as well. If we have a look at the boards on the inside, again, you can see much higher as the solar loading affects the unit. Imagine this a vehicle is parked outside and is baking in the sun all day. These are the sorts of temperatures that we could expect after a long heat soak in the sun. And let's have a look at what that actually looks like. So let me stop this guy and jump over to Flowtherm. So this is the other version of Flowtherm. This is Flowtherm XT. And what this allows you to do is deal with more complex geometries. So you can see here, this part is cylindrical in nature. You've got some round cameras and sensors on the inside. And it looks more CAD-centric as modern thermal analysis tools do. It does very similar things to Flowtherm in terms of electronics and the heat transfer. And we can have a look at the results by looking at things like the natural convection on the outside of the unit. There is some radiation happening as well, so we can have a look at the body of the part. Now this is showing the solar heat flux, so this is showing you how much heat is being absorbed into the part. The lower, a little bit confusingly, lower means that there is more solar absorbance, and on the rear, out of the shadow of the solar radiation, it goes down to zero, no absorbance. So you can see how the sun hits this. We can also have a look at the shadowing on the backside of the roof as well. Now I can also change the value to solid temperature as well. And this will now show us the temperature plot on the front of the unit, again combined with the fluid flow to give you an overall picture of the performance of this LiDAR. Next, let's look at the sensor fusion box. I think this is probably the most interesting of the electronics cooling examples that we're looking at here. So there's a few different ways that you could cool your sensor fusion box. You know, modern day, well, we're still at the start of the revolution. So sensor fusion boxes tend to be very, very high power dissipation. If you think about the amount of data that has to be received and processed by a sensor fusion box, tens of thousands, maybe even hundreds of thousands of signals per second entering this device. It has to be processed by a ASIC or an FPGA that's mounted inside the unit. And then, you know, this vehicle has got to be reasonably, you know, last maybe at least 10 to 15 years. And if you think about the position of where these sensor fusion boxes will be, maybe they'll be under the hood, maybe they'll be in a trunk, maybe they'll be even under the passenger seat, right? So there's a lot of different scenarios that the thermal engineer has to design for, right? If you think about under the seat, maybe someone stuffs a jumper under there, right, and forgets about it, and that blocks all the airflow. But still, this box has to survive for 10 to 15 years, or at least out of the warranty stage. So various ways that we can keep these electronics reliable. We can use water cooling. We can also use air cooling with forced convection will absolutely be necessary with the high power dissipation. So we're going to be dealing with moving parts no matter what. And for this example, we're going to be looking at a Minnow board turbot. So this is a kind of a competitor to Raspberry Pi, but I just want to show you the workflow going from PCB design all the way through into Flowtherm and how we can deal with some of the PCB thermal design considerations such as thermal vias or even copper pores on the PCB. Now this is actually a very low power board, but it serves the example of probably where most of the industry will be going, especially with electric vehicles. We need low power drain, you know, to increase driving range, driving time. And it's very small, maybe again about 3 inches square, and we'll have a look at that. So here's our PCB. We can see some of the main components. There's some memory modules down here. You can see the main CPU. Again, this may be an ASIC, this may be an FPGA, but we can see about a 10-watt power dissipation. And then this PCB with various connectors will be mounted somewhere in the vehicle. So let's say we're going to be mounting it in the trunk on the firewall using some adhesive or thermal pad, and we have the gravity in this particular direction. We're going to be looking at 4 different examples. The baseline will just be the PCB in the box with no connection to the edges or the enclosure. Then we're going to be looking at the additional thermal pads. Then we'll have a look at adding a potting compound. So one of the main killers of electronics in the modern day is vibration and thermal. So when things vibrate, you can get fatigue on solder joints, for example. Potting the entire PCB will stop anything from moving and lock everything in place. So we'll add a potting compound. And then what happens when we have the potting compound and external fins to increase airflow as well? So again, various things that we can have a look at with thermal analysis. So looking at the results, in the top left, we can see, again, the PCB in the box without any sort of connection. The temperature is way beyond unacceptable. 211 degrees C, that's not going to survive very long, seconds if that. And then as we start to add thermal pads, we knock off 100 degrees C. Again, I'm not too happy with that. I think that's not going to be reliable for the lifetime of the vehicle. If we pot it, we again pull down the temperature of not just the main CPU, but all the other components have got good thermal conduction to the outer edges of the enclosure. And then adding the heatsink brings the temperature down very significantly as well. So we can really understand and quantify the deltas between the design changes to guide us in which direction we should go for our thermal strategy for our electronics. If we look at the outer enclosure temperature, so this is the temperature touching our bulkhead here, we can see a fairly uniform temperature, central temperature about 211. Okay. Oh, sorry. And then as we add thermal pads, potting compound, we start to get hot spots, cooling down significantly as there's a good thermal conduction there now. Okay, and I'm just going to jump over to Flowtherm just to show an example of how this works. So I'd like to start with the expedition layout. So Flowtherm can actually read very, very detailed PCB information from the vast majority of layout tools out there. This is Expedition from Mentor Graphics, but we can export this as an ODB++ design, which we can read directly into Flowtherm. So if I jump over to the Flowtherm model and open up the Flow EDA bridge, then we are able to actually import the PCB with all of the, so here's our ODB++ archive. And let's just jump over to my turbot PCB. And what this does is it gives me the board directly from the design system, and then I can then start to manually add more information about the components. So for example, it will give me the board shape, the component location, and then it's up to me to add thermal information about the component. So here's my CPU1. I can, for example, make this a 10-watt component. If I do have let me just open my library. So if I do have a very detailed thermal model, maybe from a manufacturer, then I can replace this with a library item. This is the most critical one. You don't need to do it with all of them, but let's just pick a PGA, for example. This might be too big. Yeah, it is too big, but we can see now that we have this very detailed CPU model that's been sanctioned by the manufacturer, provided by the manufacturer. What this also gives us is, using the ODB++, is the layer information as well. So you can see this is a 12-layer PCB, very high density. We can see the layer thickness and the percentage coverage of copper on each of those layers. But if I actually process the layer, I can see what the tracing looks like. So underneath my CPU, you can see it's very black. That means there's a lot of copper under there. There's a lot of vias. And if I process this board now, then I can localize the amount of copper underneath that PCB, and it's going to have a higher concentration, a higher conductivity underneath that particular component. And that's the same for all of the layers. If we have a look at layer 2, for example, that maybe this is a ground plane, but you can see it's almost entirely black, that's going to be very, very conductive. And you can use vias to pull heat down and spread in those power and ground planes. And if we have a look at the last trace layer as well, we can see the copper there, and I can create these patches. And now we have a more detailed board. Now, jumping back into Flowtherm proper, we can have a look at our PCB. If I just focus on the PCB only and come over here, so here we have our board with all of our components on there, and I can select that and actually color that by temperature now. And let me just auto arrange that, right? And we can get a feel for where the hotspots on the board are going to be. There's my CPU. If I mouse over, 97 degrees on the edge of the PCB, 74.4, and we can get a feel for what the temperature on the PCB is going to be. If I go back to the main assembly and choose my enclosure and thermal enhancements, I can plot the temperature on these parts as well, and I can see where the hotspots are going to be. I can also impose the airflow as well, and again animate that to get a feel for what the airflow and the temperatures are doing on my enclosure. So to summarize, we've provided a very, very brief introduction to autonomous vehicles and some of the basic system architecture in terms of some of the sensors and the processing units. We've explored thermal design considerations as related to natural convection environments, transient responses to changing environments, again, moving from natural to forced convection, looked at the impact of solar loading and what sort of treatments that we can apply to the outer surfaces to increase heat transfer and reduce temperatures. Looked at sealed systems, so PCBs in enclosures, and what we can do to increase the heat transfer to the outside towards the ambient. So with that, if you would like a bit more of a custom demonstration or a custom presentation at your company, we would be happy to do this. Here's the contact details for EDA Direct. And Kang, maybe you'd like to say a few words.
Yes, thank you, Richard, for the presentation. And as Richard mentioned, this is a brief introduction to the capabilities of the tools that we have. There are a lot more things that we can, go deep down per your requirement. So contact us. I've given some contact information in the chat window. So feel free to do that, and we will look at your particular analysis requirement. Which might include further meshing, gridding, and geometry handlings and of your particular design. So at this time, want to open up the floor for any general questions from the audience based on what you've seen so far. Okay.
Yeah, if you could type the questions into the chat box, that would be great. And Kang, are there any questions at the moment?
There isn't any question yet, but one thing I wanted to ask you to elaborate for a customer is that you show a static design. Can we can you talk something about a rotating lidar?
Yeah, absolutely. I was kind of expecting that question. So we do have the ability to look at rotating regions. So over here, for example, we can add rotation onto this LiDAR. So basically, as this turns, the solar loading will hit all of the surfaces, and you'll get more of a uniform temperature on the device. It is more computationally expensive to do, right? Because we're actually physically rotating this in a sort of a static frame. So that's why I didn't do it in this very simple example, but yes, we can do rotating LiDARs. The alternative, another little simulation trick that you can do is rather than rotating the LiDAR, you can actually rotate, for example, the solar loading angle, right? So that rotates around the device rather than the device rotating. It'll give you very, very similar results.
And also, one thing I think a customer would benefit from the discussion is, can you say something about parametric analysis?
Yes, I can. So if you are looking to do variance analysis or even optimization, then we do have variation study capability. So we can start up the parametric study, for example, and then you can add either geometric, i.e. CAD dimension parameters, or simulation parameters such as heat loads, for example. So you can set up the base case model, add in some input parameters, and then the software will solve a series of scenarios based on that. Let me just see if I can put one in real quick. So let's just add the material, for example, and let's just choose a few different materials. Okay, that'll do, accept that. It will then solve the same model with 3 different materials, for example, and then give you the temperatures of the parts based on the changes that you've made. So you can perform optimizations and what-if studies using the parametric study.
Okay, great, thank you. There's a question from the audience. How do you define a reasonable H coefficient for air under natural convection?
Good question. Okay, so that's one of the benefits of doing CFD. It calculates the heat transfer coefficient for you. So based on the flow parameters, in this instance, it's just natural convection driven by gravity. So it will plot the external heat transfer coefficient on the surface for you. So for example, I'm just looking at temperature here. If I change down to the heat transfer coefficient, it will show me how effectively this part is moving heat into the air, right? So you can see maybe there's some, it's touching over, the PCBs are touching over here, but it's showing you the heat transfer coefficient in watts per meter square Kelvin, ranging between 0 and 8. And that's what I typically expect from natural convection. I'd say about 5 watts per meter Kelvin is typical. For forced convection, it's an order of magnitude larger, 50 to 100 watts per meter square Kelvin.
And I would think, Richard, that by doing a parametric sweeping, you can explore the ranges of these heat transfer coefficient, and then decide for yourself what environment the product is finally in, and then kind of guide you in that boundary. Is that true?
I mean, yes, the heat transfer coefficient, the H, is not something you need to set. It's the result of the simulation based on the airflow around it. So
Yeah.
you can set it if you want. You could, if you set it, then you don't have to simulate the air on the outside, and that could save you a little bit of time. Yeah, you could certainly use that as an input condition for the parametric study.
Great. Anyone else from the audience has any additional question for Richard? We'll stick around for a few more minutes to entertain questions. So again, if some of these need to be discussed in more detail, because your design is very particular to some requirement, contact us, send me an email. Okay. There is one question. Is there a PowerPoint and recording available later? Yes, there is. So I have provided the email address in the beginning. Check the chat window. Just send us that email and we'll send you that PowerPoint and the recording. Okay. Again, we remember we have multiple solutions here for you guys. Whichever is most comfortable for you. If you like to stay in the native MCAD environment, bring in SolidWorks files, ProE, Inventor, all kinds of formats on the mechanical side, we do support step, ages. And then on the PCB side, as Richard showed, we can bring in the ODB++, which is preferable, and everybody can generate that. So there are multiple ways of bringing in the files, and then you can operate in whichever ways you like. Okay. Any other question from the audience? Okay. So I think we'll end the webinar here. And again, thank you for attending. Please check our website, www.edadirect.com, for upcoming sessions, webinars, seminars, and workshops. We also have recordings and demos of various tools that we sell. So go there, register, and you can have access and watch all these videos that we record with actual tools. And with that, thank you, Richard, and have a good day, everyone.
Thank you. Goodbye.